Right, we'd like to move into the next part of our unit. So this is where we're going to do the bulk of the work, and this was like our introduction to kind of radioactivity, and we're starting in the whole nuclear physics aspect. So we're going to look at things like half-life, nuclear decay, and nuclear reactions. So the first thing is, let's talk about the nucleus. So Rutherford in his gold foil experiment, he determined that the nucleus accounted for about 99.9% of the atom's mass. Now, Rutherford went on a little further in atomic physics to do some more experimentation. So what he had figured in this new experiment is that what happened when he bombarded nitrogen gas with alpha particles. So what he had noticed is that some of the nitrogen gas transmuted, which is a fancy way of saying it changed to another element. So this nitrogen gas transmuted into oxygen, and some hydrogen nuclei were produced. So what Rutherford was able to conclude is that the presence of those hydrogen nuclei meant that they were fundamental to all constituent nuclei. So eventually we gave this hydrogen nuclei a name. This is what we now call the proton. Now, it was a huge advancement, but it wasn't quite enough. The protons account for most of the mass, it cannot account for all of the mass in the nucleus. There was something missing. Rutherford proposed the idea that there was a neutral particle called a neutron, and it had roughly the same mass as a proton, but it wasn't detected. So it existed in theory on paper. There wasn't any experimental evidence at the time to support that. And that has to deal with the fact that a neutral particle is not going to interact with magnetic nor electric fields. So that adds a little bit of the challenge on it. Eventually, a gentleman from the United Kingdom named Sir James Chadwick, he did some experimentation and showed that the neutron did indeed exist, and it had a mass about 0.1% greater than that of the proton. So because he discovered the neutron experimentally, Chadwick was given the Nobel Prize in 1935. So when we're doing nuclear physics, we're going to have some nuclear notation, and we're also just going to have some terminology we want to be aware of. So protons and neutrons, the collective of those together is what we refer to as nucleons. The reason for that is protons and neutrons both live inside the nucleus. So nucleons refers to the total number of protons and neutrons. There's also a few other things that we have to be aware of in terms of notation. We're going to have this atomic number, also labeled as Z. So the atomic number tells us the number of protons in a nucleus. This is read directly from the periodic table. So the periodic table is organized by atomic number. So hydrogen's 1, helium's 2, lithium's 3, so on and so forth. So how we organize the periodic table is actually by atomic number. The neutron number gives us the number of neutrons in a nucleus. And then the atomic mass number, this is the total number of nucleons in a nucleus. For the most part, the atomic mass number, it's usually given. If you're having troubles finding something on the periodic table, you know when you have the mass on there, like it's the molar mass in grams per mole, the molar mass is the average of the molar masses of all the isotopes and a weighted average. Your average molar mass should be close to the atomic mass number. So for example, if you're given like uranium-235 and you're having a hard time finding uranium on the periodic table, look for a molar mass somewhere in the 235 region. It's not going to be exactly that, but it should guide you to where you should search on the periodic table. So generally when we write things in nuclear notation, we're going to write it in this form AZX. So A is that atomic mass number that we've talked about. Z is going to be our atomic number, and then X is going to be the chemical symbol for the element, which is going to be off the periodic table. We could also write it like AX, just because the chemical symbol implies the Z value, so we don't actually have to put the Z value there, but in physics, we usually put the Z value. Chemistry, they sometimes ignore it. Now, an isotope, I mentioned this earlier, let's talk about it a little bit more now. So it's a variant of a particular chemical element. So if we're talking about a specific element, it always has to have the same number of protons, because the number of protons kind of defines what element we have. But an isotope is something where we have different number of neutrons. So for example, looking at the very first element in the periodic table, hydrogen. So ordinary hydrogen that we know and love, ordinary hydrogen is just going to be a single proton and no neutrons. But if we start to add a neutron to that, we're going to get deuterium, we add another neutron to that, we're going to get tritium. Deuterium and tritium have applications in nuclear physics. So these are all still hydrogen at the end of the day, but they all have different properties. And that's the main thing with an isotope. We keep the same number of protons and electrons, but we're going to have different number of neutrons. And those changing number of neutrons is going to change the chemical properties, it's going to change the physical properties of that element. And this is one of those things where certain isotopes may be radioactive versus, certain isotopes being non-radioactive. So when we talk about carbon-12, like the kind of carbon we know and love, that is non-radioactive. An isotope of that carbon-14, however, is highly radioactive. We use that for radiocarbon dating to determine the age of things. So that's the thing with the isotopes. Same number of protons, different number of neutrons. That allows us to change those chemical properties. Now, with this, we are going to be dealing with some very small masses. We know that the base unit for measuring mass in the SI system is the kilogram, and that's great for everyday objects. Atomic level, not particularly useful. Well, I shouldn't say it's not useful. It's just writing like times 10 to the minus 20s, blah, 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 kilograms over and over and over again is going to get frustrating. So we want to have a unit that helps us out. So for subatomic particles, we have this thing called the atomic mass unit, or the U. It is defined as being exactly 1/12 of the mass of a carbon-12 atom. So the value of U is this. So on the data sheet, we're just going to use this 1.66 times 10 to the minus 27 kilograms. In atomic physics, you are going to see the atomic mass unit used significantly. It is much more easy to work with than having to write all of that scientific notation. Now, in the nucleus, we want to look at some forces that kind of bind it together. So with the exception of hydrogen, all nuclei are going to have 2 or more protons and a number of neutrons. So we know that like charges are going to repel one another. So if we have 2 protons or more in a nucleus, they instinctively want to repel due to that electrostatic repulsion force between them. So there has to be some force that overcomes that repulsion to hold everything together. We'd like to look at that though. So what is going to keep it together? The only other force we've actually studied in physics on a great detail is the force of gravity. So let's see if the force of gravity can bind the nucleus together. What we'd like to do is we'd like to look at the ratio of Fg to Fe. If that ratio is at least 1 or greater, that tells us that the force of gravity is either equal to the electrostatic force or greater. It can bind the nucleus together. Let's check how that works. So the force of gravity divided by the electrostatic force. So in Physics 20, the force of gravity, we did Newton's law of universal gravitation. So we're going to have G mass proton divided by the distance between them squared. We're just going to assume for 2 protons. And then the electrostatic force is going to be K q proton divided by the distance between them squared. All right, well, the distance between them is going to cancel out, so that's certainly nice. Now, mass proton, that should be mass. So mass proton times mass proton is just going to be mass of the proton squared. And then q proton times q proton is also going to be q proton squared. So to find that ratio of the gravitational force to the electrostatic force, we have this G mass proton squared divided by K q proton squared. So let's look. So the universal gravitational constant is at 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. The mass of a proton is 1.67 times 10 to the minus 27 kilograms. So all this information is on your data sheet. We'll square that. Coulomb's constant is 8.99 times 10 to the 10 to the positive 9 Newton meters squared per Coulomb squared. And then we have our charge on the proton is 1.60 times 10 to the minus 19 Coulomb, and then all squared. So let's just check the units. If this is a ratio of forces, at the end of the day, we should not actually have any units. It should be dimensionless. So let's look at this. So I have kilograms squared. That will cancel that kilogram squared here. Okay, that's certainly good. We want that. And then we have Coulomb squared is going to take care of that. Coulomb squared. Whoops, I don't want to cross out that part. Now I have Newton meters squared up top, and I also have Newton meters squared in the bottom. So those are also going to cancel out. So at the end of the day, I actually have all of my units canceling out. That's good. This is going to be a dimensionless number. We expect that. So this dimensionless number, it's going to be about 8.08 times 10 to the minus 37. That is really small. So what does this mean? Let's put this into context. What this means is that the force of gravity is approximately 38 orders of magnitude weaker than the electrostatic force. The force of gravity is going to do nothing in this case. It is so incredibly weak. So the gravitational force is not going to keep the nucleus together. It's so inconsequential. What's actually going to keep it together is another of the 4 fundamental forces of the universe that we have not yet talked about. So this force that's going to keep the nucleus together, that's going to keep all the protons and all the neutrons together, this is referred to as the strong nuclear force. So the strong nuclear force, as the name implies, is the strongest of the 4 fundamental forces. But it has a bit of a catch. It's got a really short range. So it's only able to have an effect on particles that are just a few femtometers apart. So when we say femtometer, we're talking 10 to the minus 15 meters. After we exceed that distance, the strong force becomes negligible. So it only applies on a really small distance. We're going to talk more about that later.